NEC Article 110.3 B allows two conductors to be connected to a single pole circuit breaker that is rated for the ampacity of both conductors. NEC Article 408.31 requires that three-phase circuit breakers be used to disconnect all ungrounded conductors of a three-phase system. Connecting only two phases to a three-phase breaker can create an unbalanced load, potentially leading to overheating or damage to the breaker or system components. The use of a single-pole breaker disconnects only one phase, potentially leaving the other two phases energized and creating a safety hazard. If one phase fails, the remaining two phases will continue to provide power, increasing the risk of electrical accidents. Installing two wires on a three-phase breaker is unprofessional and does not adhere to industry best practices. It can create a false sense of safety and compromise the integrity of the electrical system. It can be difficult to troubleshoot and repair issues if the system is not properly configured. Firstly, use a properly rated three-phase circuit breaker. This will ensure proper protection and disconnect all phases of the system. Secondly, do not use single-pole breakers to connect two phases to a three-phase circuit. This is a hazardous practice that should be avoided. Thirdly, consider the implications of unbalanced loads when selecting circuit breakers. Ensure that the system is designed to handle the expected load without creating an unsafe condition. Based on the available code and safety considerations, it is generally considered inappropriate to install two wires on a three-phase breaker. Using a three-phase breaker is the safer and more professional option. An unbalanced load in a three-phase system occurs when the current flowing through each of the three phases is not equal. This inequality can arise due to various factors, leading to potential problems within the electrical system. Firstly, single-phase loads unevenly distributed across the three phases. Many residential and commercial buildings utilize single-phase loads such as lighting, appliances, and single-phase motors. If these loads are not evenly distributed across the three phases of the system, it creates an imbalance. Secondly, faulty equipment can cause imbalances. Malfunctioning equipment, such as a failing motor winding or a short circuit in one phase, can draw excessive current from that phase, leading to an unbalanced load. Thirdly, transformer issues can lead to imbalances. Problems within the distribution transformer, such as unequal impedance in the windings, can contribute to unbalanced current flow. Fourthly, open phases can cause imbalances. An open phase, where one of the three phases is disconnected or has a high impedance connection, results in a severe imbalance as current can only flow through the remaining two phases. The consequences of unbalanced loads can be significant. Firstly, overheating of equipment is a concern. Unbalanced currents cause higher current flow in some phases, leading to increased heat generation in conductors, transformers, and motors. Overheating reduces the lifespan of equipment and can lead to failures. Secondly, voltage drops occur with unbalanced loads. Unequal current distribution causes voltage drops in the heavily loaded phases, affecting the performance of voltage-sensitive equipment. Thirdly, increased losses are due to unbalanced loads. The overall efficiency of the electrical system decreases as unbalanced currents result in higher I2R losses in conductors and equipment. Fourthly, premature equipment failure is a consequence. The stress caused by unbalanced conditions accelerates the degradation of insulation and other components, resulting in premature failure of electrical equipment. Fifthly, nuisance tripping of circuit breakers may occur. Overcurrent protection devices may trip due to the higher currents in some phases, leading to unnecessary downtime. To mitigate the problems associated with unbalanced load, several strategies can be employed. Firstly, load balancing is essential. Distribute single-phase loads as evenly as possible across the three phases to minimize current imbalances. Secondly, regular maintenance and inspections are necessary. Conduct routine inspections of equipment to identify and address any potential issues that could lead to imbalances. Thirdly, use phase balancing equipment. Install equipment such as automatic voltage regulators or static VAR compensators to actively balance the load and maintain voltage stability. Fourthly, proper transformer selection is important. Choose transformers with balanced impedance characteristics to minimize imbalances caused by the transformer itself. Fifthly, implement monitoring systems to help. Use monitoring systems to continuously track current and voltage levels in each phase, allowing for early detection and correction of imbalances. By understanding the causes and consequences of unbalanced loads, and by implementing appropriate mitigation strategies, it is possible to maintain a safe, efficient, and reliable three-phase electrical system. The concept of phase imbalance in a three-phase system refers to a condition where the voltages or currents in the three phases are not equal in magnitude or are not equally spaced in time by 120 electrical degrees. This imbalance can lead to a variety of problems in electrical equipment and systems. Voltage imbalance is defined as the maximum deviation from the average voltage of the three phases divided by the average voltage expressed as a percentage. Current imbalance is similarly defined as the maximum deviation from the average current of the three phases divided by the average current expressed as a percentage. Several factors can cause phase imbalance in a three-phase system. Firstly, unbalanced loads contribute to this issue. Unequal distribution of single-phase loads across the three phases is a common cause. If one phase is heavily loaded compared to the others, it will draw more current, leading to voltage drops and current imbalances. Secondly, faults in equipment create imbalance. Short circuits, ground faults, or open circuits in one or more phases can cause significant imbalances in both voltage and current. Thirdly, transformer issues play a role. Problems such as unequal impedance in transformer windings or faults within the transformer can contribute to phase imbalance. Fourthly, long distribution lines can create problems. Unequal line impedances due to variations in conductor size, spacing, or transposition can lead to voltage drops that differ from phase to phase. Fifthly, single phasing is a cause. The loss of one phase in a three-phase system, known as single phasing, results in a severe voltage and current imbalance. The consequences of phase imbalance can be detrimental to electrical equipment and system performance. Firstly, overheating of motors is a risk. Unbalanced voltages and currents can cause increased current flow in some phases of a motor, leading to overheating of the motor windings and reduced motor life. Secondly, reduced motor efficiency occurs. Motors operating under unbalanced conditions experience reduced efficiency and increased energy consumption. Thirdly, increased vibration and noise results. Unbalanced voltages and currents can cause mechanical stress and vibration in motors and other rotating equipment, leading to increased noise levels and potential damage. Fourthly, transformer overheating is a concern. Unbalanced loads can cause increased losses and localized heating in transformers, reducing their lifespan and potentially leading to failure. Fifthly, malfunctioning of sensitive equipment happens. Sensitive electronic equipment and control systems may malfunction or operate erratically when subjected to imbalanced voltages. Sixthly, tripping of protective devices occurs. Overcurrent and overvoltage protection devices may trip unnecessarily due to the unbalanced conditions. To mitigate the effects of phase imbalance, several strategies can be implemented. Firstly, load balancing is essential. Distribute single-phase loads as evenly as possible across the three phases to minimize imbalances. Secondly, regular maintenance is necessary. Conduct routine inspections and maintenance of equipment to identify and address any potential issues that could contribute to phase imbalance. Thirdly, use power factor correction. Install power factor correction capacitors to improve the power factor and reduce current imbalances. Fourthly, implement voltage regulation. Use voltage regulators to maintain stable voltage levels and reduce voltage imbalance. Fifthly, use monitoring systems to help. Implement monitoring systems to continuously track voltage and current levels in each phase, allowing for early detection and correction of imbalances. Sixthly, use properly sized conductors for the electrical wiring. Using appropriately sized conductors helps in balancing voltage drop. A failure of one phase in a three-phase system, also known as single phasing, occurs when one of the three phases is interrupted or lost. This can happen due to various reasons, leading to significant problems for equipment connected to the system. The causes of single phasing can be varied. Firstly, blown fuses can create the situation. A blown fuse in one of the phases can interrupt the current flow, causing single phasing. Secondly, tripped circuit breakers can be the cause. A tripped circuit breaker due to overload or fault in one phase can lead to the loss of that phase. Thirdly, damaged wiring and connections can lead to problems. Broken wires or loose connections in one phase can interrupt the current flow. Fourthly, equipment failure may occur. Failure of equipment such as transformers or switchgear components in one phase can result in single phasing. The consequences of single phasing can be severe, particularly for three-phase motors. Firstly, motor overheating is a concern. When a three-phase motor operates on single-phase power, it can draw excessive current in the remaining phases, leading to overheating of the motor windings. Secondly, reduced motor torque results. The motor produces significantly reduced torque when operating on single-phase power, which can cause it to stall or fail to start. Thirdly, motor damage can occur. Prolonged operation of a motor under single-phase conditions can cause irreversible damage to the motor windings and insulation. Fourthly, equipment malfunction is a risk. Other three-phase equipment, such as transformers and electronic devices, may malfunction or be damaged by the unbalanced voltages and currents resulting from single phasing. Fifthly, safety hazards may arise. Single phasing can create unsafe conditions due to the potential for equipment failure, overheating, and electrical shock. To prevent or mitigate the effects of single phasing, several measures can be taken. Firstly, use properly sized fuses and circuit breakers. Install properly sized fuses and circuit breakers to protect against overloads and faults that can lead to single phasing. Secondly, implement phase loss protection. Use phase loss relays or monitors to detect single phasing conditions and automatically disconnect the affected equipment. Thirdly, perform regular maintenance. Conduct routine inspections and maintenance of electrical equipment to identify and address any potential issues that could contribute to single phasing. Fourthly, use redundant systems. Employ redundant power supplies or backup generators to provide power in the event of a phase loss. Fifthly, use monitoring systems to help. Implement monitoring systems to continuously track voltage and current levels in each phase, allowing for early detection and correction of single phasing conditions. Single phasing is a serious issue that can have significant consequences for electrical equipment and systems. By understanding the causes and implementing appropriate preventive measures, it is possible to minimize the risk and impact of single phasing. Electrical safety is paramount when working with electrical systems, and several fundamental principles should always be followed to ensure personal safety and prevent electrical hazards. Firstly, always de-energize equipment before working on it. Always disconnect power to the equipment or circuit you are working on by turning off the appropriate circuit breaker or switch. Verify that the power is off using a reliable voltage tester before touching any wires or components. Secondly, use lockout-tagout procedures when necessary. When working on equipment that cannot be easily de-energized, use lockout-tagout procedures to prevent accidental energization. This involves placing a lock and tag on the disconnecting device to indicate that the equipment is being worked on and should not be turned on. Thirdly, wear appropriate personal protective equipment. Always wear appropriate personal protective equipment, including safety glasses, insulated gloves, and appropriate clothing when working with electrical systems. This will help protect you from electric shock, burns, and other injuries. Fourthly, use insulated tools only. Use tools with insulated handles that are specifically designed for working with electrical systems. This will help protect you from electric shock if you accidentally come into contact with a live wire. Fifthly, maintain a safe working distance. Maintain a safe working distance from energized equipment and wires. Avoid touching any exposed conductors or terminals, and use caution when working in confined spaces where it may be difficult to maintain a safe distance. Sixthly, never work alone if possible. Avoid working alone on electrical systems whenever possible. Having another person present can provide assistance in case of an emergency and can help ensure that safety procedures are followed. Seventhly, be aware of your surroundings. Pay attention to your surroundings and be aware of any potential hazards, such as wet floors, overhead power lines, or other electrical equipment. Eighthly, follow all safety regulations and procedures. Always follow all applicable safety regulations and procedures when working with electrical systems. This includes following the National Electrical Code, as well as any specific safety rules or guidelines established by your employer or local authorities. Ninthly, if not qualified, do not perform the work. Only qualified and trained personnel should work on electrical systems. If you do not have the necessary training and experience, do not attempt to perform electrical work. Tenthly, be aware of arc flash and blast hazards. Arc flash and arc blast are dangerous phenomena that can occur when working with energized electrical equipment. Be aware of these hazards and take appropriate precautions to protect yourself, such as wearing arc-rated clothing and using appropriate shielding. By following these fundamental principles of electrical safety, you can significantly reduce the risk of electrical accidents and injuries. Always prioritize safety when working with electrical systems, and never take shortcuts or compromise on safety procedures.